Okay, all right. So here we are again in chapter 2. We were talking about how to understand equations, and again in a two-variable context. This is a high school algebra thing. It's parabolas and hyperbolas and all that business. And you've already seen a million examples of those kinds of things. So we're exploring the harder problem of what if you have equations of three variables? What do these things look like? And last time we talked about the method of cross-sections, and roughly speaking, the strategy there is let's take a three-dimensional question. What does this surface in space look like? And let's look at individual cross-sections, thus turning it into a two-variable problem that we already know how to solve, and then we just have to kind of piece those two-variable curves back into a three-variable surface. Okay. All right. So lots of artistic challenges. You end up with a bunch of pictures that look like that and this, and you got to figure out how they all fit together. Okay. All right. So now I'm going to show you another tool for your toolbox for this kind of thing. So sometimes it might be that the equation that you're looking at is kind of familiar looking. Not exactly something that you've already understood, but maybe it looks a lot like something you've already understood. Okay, so specifically, let's start off with an equation of this form here, and let me point out that really this means let's consider all possible equations of three variables. If you think about it, an equation of three variables, bunch of stuff equals bunch of stuff. Take whatever's on the right, subtract it over to the left, now you've got some function of three variables equals 0. Right? So this is a standard and very convenient way to think of an equation of three variables. So I want to consider the question of what happens. Let's suppose that I know what the solution set to this looks like. This is a familiar equation with a familiar surface. What happens if in that equation, everywhere I see an x, right, I replace it with x plus 1. So the resulting equation is going to look a lot alike this one that we started with, but with this key difference that every x has been kind of erased and replaced with x plus 1. So we want to know what does that do to the solution. So I'm going to come down here to where the picture is and sketch out an argument here. So let's suppose we know our original surface. Our original surface, let's say, is S. So let me write that down here. So here we have f of x comma y comma z equals 0. And I ask the question, okay, what would happen if we replace everywhere we see an x? We replace that with x plus 1. That's going to give us a new equation, f of x plus 1, comma y, comma z equals 0. Right? This is what we want to understand. We don't currently know. What does this look like? Okay, so here's the big observation I want to make. That is that every point that satisfies this equation here, if you think about it, a point x, y, z that satisfies that blue equation, that point, if you add 1 to it in the x coordinate, gives you a trio of coordinates. First coordinate, second coordinate, third coordinate, and when you plug into f, gives you 0. In other words, when you add 1 to the x coordinate of this green point, you get a solution to this equation. Okay, so now let's think about that geometrically then. What that means is that these green points, x, y, z, that when you add 1 gives you a solution to the equation, those green points, when you add 1 to their x-coordinate, when you shift them by 1 in the direction of the x-axis, you get a point that's on our original surface. So that means that these green points here are points like this, such that when you add 1 to their x-coordinate, you get points on there. How are we doing? Does everybody kind of see? So what we have here is, here I have some algebra, and then here I have the corresponding geometric picture of what's going on in the algebra. I'm going to take a pause before we go on, if anyone has any questions. And exactly what we're going to do with this and what is the consequences, we'll get to that momentarily. Mm-hmm.
So S prime is right.
You haven't gotten to that yet. Yeah, so you're jumping ahead a little bit, right? So yeah, one of the disadvantages of having the picture already drawn is that yeah. So let's pretend for the moment we haven't figured out that S prime thing. Everybody good? So the assertion that I'm making right now is that a point XYZ that satisfies this equation must be a point that when you add 1 to it gives you a trio that fits in like that. All right. So now you're going to the next step. That means that these green points are points that when you shift them in the X direction give you these points on the surface S. Another way of saying that is the collection of all possible green points is the collection of all points that when you shift them in the X direction land on that purple surface. And I claim that's also going to be, it's going to look a lot like that purple surface. Like so. And I think I kind of trampled my little yellow arrow there. There we go. Okay, and another way to say that, this green surface is the surface which, when you shift it positively in the X direction, gives you the purple surface. Another way to say that is you can deduce the green surface by taking the purple surface and shifting it backwards in the X direction, and that will yield the green surface. And that's what I have in this picture down here. Take your purple surface here. This process of replacing everywhere you see an X, replacing that with X plus 1, that process effectively shifts the surface backwards in the X direction. Like that. Okay, it's very often students are confused by this and think, well, isn't this backwards though? Shouldn't when you replace X by X plus 1, I see a plus 1. Doesn't that mean that the X is getting bigger? Shouldn't the X coordinates increase by 1? Well, it depends on how you look at it. The X coordinates are increasing by 1 here. Right? I mean, these green points, the points that are on the green surface, are points that when you increase X by 1. Yes. The point is, you increase points X coordinates by 1 to result in the purple surface, your original surface, not from your original purple surface. And so, in effect, that plus 1 moves things backwards. Okay, let me show you an example. Let's get some actual algebra on the page here. So let's look at this equation right here. How can we understand that equation? Now, good news, we already know the answer to this. Right? I could easily interpret this as this is the collection of all points that are a certain distance away from a certain center. So this is a sphere. And here, let me write this a little bit differently. This is the collection of points whose distance, the distance from XYZ to -1, 0, 0 is equal to 1. All right, note the minus signs here because that's a plus sign. We need this minus sign because it needs to be a distance. Therefore, there has to be a minus sign there. So this is the collection of points whose distance is 1 from -1, 0, 0. Namely, this is a sphere centered at -1, 0, 0. Okay, so that surface we know is this. It's a sphere centered at -1 on the x-axis. Right, so one way we could view, now again, that's just a that's a different kind of a reference. I like examples sometimes where we know what the answer is supposed to be, so that you can have this feeling of confirmation when you go through the new process that we're just discussing. Let's view this instead as the result of a replacement. Here, I'm going to say this is my original surface. My previously understood surface. We already knew this surface was what you get with x squared plus y squared plus z squared equals 1. This is more familiar, right? And notice that algebraically, when you take this equation and when you do this to it, everywhere you see an x in that purple equation, if you replace that with x plus 1, then what you get is our green equation. And you can see right here the x being replaced with x plus 1. Everybody on board? So I'm going to call this a confirmation, right? I mean, what happens when you transform the variables like this? In this equation, you replace x with x plus 1. Our assertion was that shifts the surface backwards in the x direction. That it shifts like that. Shifts the whole thing, and therefore also the center back on the x-axis. And we know that was correct in this case because, well, we can take a different point of view on understanding this equation anyway. We already knew that it was going to look like that. Okay, so this example here is indicative of there's a large collection of analogous arguments that you can make, right? So instead of, what happens when you replace x with x plus 1, what do you suppose happens if you replace x with x plus a different constant? Same idea. It shifts it backwards in the x direction by whatever that is. What if you replace x with x minus a constant? It's going to shift it forward in the x direction. Same basic idea. Right? A little bit weirder. What happens if you replace x with k times x? Well, that's going to, in effect, and again, keep in mind everything kind of is the backwards of sort of what you would expect. If you replace x with k times x, that's going to then it's going to reduce all of the x coordinates by a factor of k. It's going to do what I call a squish. The whole surface is going to get squished in by a factor of k in the x direction. Likewise with y's and z's, just to be in the y and z directions. But everything is backwards. Everything is opposing what you're doing to the algebra. Okay. All right. Here's another example. Let's look at this equation. Right. Let's do it like this. Let's look at this equation right here. How would I understand this equation? And notice that it looks a lot. Algebraically, symbolically on the page. Come on, this looks a lot like x squared plus y squared plus z squared is 1. So I'm going to view this as some sort of transformation of the unit sphere. Right. But there's kind of two different transformations happening there. You see that there's a multiplication by 2, but there's also a subtraction of 1, and so this is going to be a 2-step transformation instead of a single-step transformation. And the reason I want to show you this example is because there's another sort of unexpected backwardsness that happens ultimately because of the backwardness of kind of the whole process. So here we go. Here's the process. We're going to start with our good old familiar equation there, whose solution set, again, is our familiar sphere, unit sphere, centered at the origin. Right? And now let's just think about, algebraically, what do I have to do to that equation? What are the steps that I have to do to that equation to turn it into this equation that I'm actually interested in? And having identified what the algebraic steps are, next question, well, let's just kind of follow it through. What did this algebraic step do to the solution set? And then next, what did this algebraic step subsequently do to that solution set. So we're going to go through algebraically to get to our goal, and then we're going to follow it through geometrically to get the answer that we're interested in. Does everybody see the strategy, what we're doing? Question? Yeah. Mm-hmm.
Does order matter?
Yes, that's the thing. That's going to be the moral of this story, is that the order does matter. Yeah, great question, and I'm going to totally talk about that pretty much right now, yeah. There is a temptation here, again, to think, well, we've got to do these steps in the order of operations or something. This alluring seems like you ought to do order of operations. And so there's temptation to do the multiplication, the squish first. And I claim that would be a bad choice. So first let's do it my way, and then I'll show you what you run into if you do it the wrong way. Okay. So I suggest that we first replace everywhere we have a y, let's replace that with y minus 1. As you can see, I've done there. Replace y with y minus 1. Having done that, in this next equation, I suggest that everywhere we see a y, we put a 2y, and now be very, very careful. Very careful. Everywhere I see a y in this previous story that I've got here, not over here, right? I'm not readjusting from my original equation, right? This is gone now. I'm done with this thing. It served its purpose. Thank you. Goodbye. You're dismissed. I don't need you anymore. I already have something that's better that I'm more interested in, and no need to ever look at that again, right? So, in our equation here, in this equation, everywhere you see a y, put a 2y, and that turns this y here into that 2y there, and notice we get the 2y minus 1 that we wanted. Right? Now there's this reflexive, students have this urge to say, well, yeah, but isn't that really kind of y there? I mean, that's, and there's this, you're looking back at the original equation, and this y minus 1 is the thing that came from the original y, and it just seems like you ought to. Don't step on that landmine, right? This original story has served its purpose. We don't need it anymore. We're not interested. It's irrelevant at this point. I know that this equation gives me that surface, and this is what I'm going to transform. So ignore all that over there. Okay. All right. So y becomes 2y. Like so. We get the equation we wanted. Now let's think it through geometrically from these steps. This first step. Wrong color. Sorry. This first step here is going to shift in the positive y direction because it's a minus 1. Shift in the positive y direction by a distance of 1, like so. Right, and then this replaces y with 2y. That's going to squish in the y direction by a factor of 2. Now, importantly, let me say that a little bit more precisely. When I say it's going to squish, I mean, what this is really going to do is this is going to take all the y coordinates of points on this surface, and it's going to replace them with y coordinates that are half as much in preparation for being multiplied by 2. Okay. So when you take the y coordinates and replace them with coordinates that are half as much, the squish happens like this. Right? Look what my hands are doing. See, where the y coordinates are 0, they don't change. The y coordinates get cut in half, so the squishing is like this. There's a temptation to think about how you would. It's a ball. The way you squish a ball, it would seem, is to squish equally from both sides. And students kind of want to leave the center where it is. Right? That's not what happens. The y coordinates all get cut in half, so the squishing also kind of shoves the center over at the same time, thus resulting in this. Whoops, green. So that center moves over a little bit as well. Yep.
If the top right sphere
Mhm.
lined up with the axis, if the edge were at 1, so
Oh.
wouldn't the edge move over?
Yep, then the edge would move over as well. Yeah, so what I should say to be more general is that when you do a squish, you're always squishing, if you're squishing in the Y direction, you're always squishing from the XZ plane. Yeah, you're squishing from wherever Y is 0. So yeah, if the edge had been at 4, then it would, when it gets squished, that edge would move over to 2. Yeah, totally. Okay, so now let's consider what would happen, just from an algebraic point of view, if we did the operations in the other order, if we did multiplication first. Let's take this Y, and let's replace Y with 2Y. Then I'd have a 2Y there in my equation. And having done that, now let's subsequently replace Y with Y minus 1, because, again, order of operations, and do the multiplication first, and next thing it says right there, subtract 1, right? But notice that when you do that, you got to be very careful about this. It's real easy to mess this up. You're replacing Y with Y minus 1, that Y, not this Y, not the thing that became the 2Y, right? So you're not subtracting 1 from the 2Y. You're subtracting 1 from that Y, and the result is 2Y minus 1, which is 2Y minus 2, which is not what we wanted. Everybody see what happened there? Okay, so it's real easy to mess this up, get it backwards, do it the wrong way. So be careful. Now, one thing you can do, and this totally fine, if you want, you'd be real clever about this, and you could say replace Y with Y minus a half. And that does indeed give you 2Y minus 1. Totally fine. This would be highly acceptable. No problem. I just think this is harder. You'd have to kind of strategize. You have to kind of reverse engineer. Wait, what is this clever amount that I need to adjust by in order to recover the exact thing? It's just easier if you do it that other way. It's my opinion. Okay. All right. Moving along. Okay. Last tool that I'm going to give you for understanding equations in 3-space is rotational symmetry, and this is very often super useful. Super useful. The world is full of symmetries. Is why. Okay. So now that said, let's recognize, right? Be completely upfront about it. Not everything is symmetric. Right? There's plenty of things that are not symmetric. Things that are symmetric are not always symmetric about every axis. Right? They're only symmetric about certain axes. So this rotation argument that I'm going to give you only applies under certain conditions. And you got to be careful about it. You can't just apply willy-nilly and say, I assert that this is a symmetric thing, and if it isn't. Okay. So we've got to be careful with the cases. Here's what we're interested in, and that is the tip-off that you have a symmetry. We're going to start off with symmetry around the z-axis. If in your equation, if you notice that x and y appear only as part of this form, square root of x squared plus y squared, that's your tip-off. Here's an example. Let's look at this equation here. X squared plus y squared minus z equals 0. And notice I could rewrite this as square root of x squared plus y squared. There it is. Quantity squared minus z equals 0. So notice that x and y don't appear in this equation anywhere else other than as part of that specific form. Everybody see what I'm talking about? All right, so let's talk about what you can deduce from this. Oh, by the way, quick observation, this little magic expression that I'm making reference to, this square root of x squared plus y squared, notice that is the distance to the z-axis. All right, if you have some point here, look at the distance to the z-axis, you have the point x comma y comma z. Over the closest point on the z-axis is 0 comma 0 comma z. That's that closest point, and this distance is square root of x squared plus y squared. Okay, so let's suppose that happens. What can we deduce? And I claim here's the idea. The punchline is going to be that the surface must be rotationally symmetric around the z-axis, which is going to be super useful for us trying to understand the surface. We'll see examples in a moment. But here's why I claim that symmetry. Suppose we have such an equation. X and y appear only as part of that special form. And let's suppose that we have a point that we know satisfies the equation and therefore is on the surface. And then let's consider a rotation of that point. Right? Now, let's think about what happens when you rotate. You have a point in space and you rotate around the z-axis, strictly rotating. The z-coordinate doesn't change. You're rotating around the z-axis. The z-coordinates don't change when you do that. Now, x changes. Y changes. But the distance from the z-axis also does not change when you rotate around the z-axis. So, let's think about the equation then. I mean, the equation, keep in mind, x and y, our big assumption is that x and y appear only as part of this form. Distance to the z-axis, square root of x squared plus y squared. Sure, these points have different x's and y's, but those different x's and y's go right into this expression and only into this expression to result in the same value, rz, for both of these points. And so as far as the algebra of the equation is concerned, these points are indistinguishable, right? These points and they're different x and y coordinates. Yeah, they give you the same value of the only ways that x and y show up in the equation. They play the same game. So if this purple point is on the surface, and keep in mind we're interested now in this green point, that is its rotation. Yes, that green point is also on the surface. Everybody good? Okay, this is a really powerful tool. Why is this powerful? Well, this turns into a dimension reduction argument for us. And so here's the next bit of the tool is to observe like this. If you have a surface that is rotationally symmetric around the z-axis, such as what I've drawn here, if you were to take a cross section in a half plane, so this is just this half of that plane. I don't mean the whole XZ plane, just this half. A half plane hinged on the z-axis, if you will, swinging like a door, if you will. This being a symmetric surface, if I simply know what that cross-section curve looks like, then that cross-section curve tells me the whole surface. If I know the cross-section looks like that, then, well, obviously the surface is what you get when you take this cross-section curve and rotate it around the z-axis. That's the nice thing about symmetry. What do y'all think about that? So, a big assertion: if your shape is symmetric around the z-axis, then your surface is simply a rotation of the cross-section curve. Yes.
Why couldn't we do this? I see that it would work, but why couldn't we do the same thing around other apps? Like this one, you set y equals.
Oh, yeah, so for right now, I just want to focus on symmetry around the z-axis and rotations around the z-axis. And you're quite right that for different surfaces, if your surface is rotationally symmetric around the y-axis, analogous argument works, totally, right? But just to kind of keep things simple, just first time through, I want to focus just on the z-axis. Is that cool?
So, like, to make this plane,
Yeah.
you set y equals to constant.
To make this plane, I'm setting y equal to 0 and requiring x to be positive.
So why couldn't you do the same thing, setting x equals to 0 and y?
You're quite right. I could totally do that, and that is another option, and you're welcome to do it that way. It's going to give you the same conclusion. Yeah. So what she's asking, in case some of you all might have not followed along, she's asking, well, can't I look in this half plane and study this cross-section curve? And wouldn't rotating this red curve give me the same surface? And yeah, absolutely. Totally. So either way is fine. Again, I'm picking one option just so that we can be, just to have one to talk about, not because it's better. Yeah. Okay. So, so here's the punchline then. Nice punchline. If you have an equation where x and y appear only in this very special form, part of square root of x squared plus y squared, if x and y appear only as part of that special form, your surface is symmetric, and therefore your surface is a rotation of this cross-section. In other words, you can just understand this one curve. Reminder, we're really good at understanding curves. That's algebra 2. You can understand that one curve, and once you understand that one curve, just rotate it around the z-axis and celebrate. I mean, you're done, right? You don't have to take a billion cross-sections and try to piece them together like some sort of complicated three-dimensional puzzle. One cross-section, rotate it, celebrate. Okay. All right, so let's see an example of this. Let's see here. Where is my good example? Here we go. So let's look at this equation. And now I'll confess, yes, we already know what this looks like. We went to great difficulty last time in understanding z equals x squared plus y squared, which of course is equivalent to this. And it was a pain. We were taking cross sections every which way, and we had these various hard to draw three-dimensional, things, and we, by halfway decent drawing at great inconvenience and a certain amount of geometric intuition, we're able to figure out that means that this is a bowl. Now watch how much easier it is using a rotation argument. X and y appear only as part of the special form. Therefore, this is rotationally symmetric around the z-axis. I can understand its cross-section. Now keep in mind, the cross-section I'm interested in, arbitrarily. I'm interested in the cross-section in this plane, this half plane where y is equal to 0 and x is greater than or equal to 0. I just want to look at that one half plane. In which case, square root of x squared plus y squared is the square root of x squared, because y was 0, which is the absolute value of x. Oh, but x is positive, so that's just x. Square root of x squared plus y squared becomes just x. So, in the cross-section that I'm interested in, this becomes just x squared minus z equals 0. That's a parabola. There's my cross-section plane. X squared minus z equals 0. That's z equals x squared. That's a really easy curve. And it's pretty straightforward. I think it's geometrically unchallenging to think about it. If you take this parabola and rotate it around the z-axis, then you get this bowl. I mean, that's way easier, I think, than making a cross-section argument. Yeah?
How did you know from x to x squared?
Oh, yeah. So the original equation was, pencil. Original equation was x squared plus y squared minus z equals 0, which I could rewrite as square root of x squared plus y squared minus z equals 0. And remember, this is what x is. Yeah. Pretty good. So, it's pretty handy. Very handy. All right, let me show you another example of this. I like this one here. Oh, is this the... You already did that one. Okay. So, let's look at this equation. And that's kind of brutal looking, right? I mean, you start thinking about cross sections. Let's set y equal to a constant here, right? Yikes! The cross sections of this would be really hard to understand. Okay. So let's make a rotation argument. Hey, check it out. X and y appear only as part of the special form. This thing's rotationally symmetric around the z-axis. I can understand this whole thing just by looking at one cross section and a half plane in which that expression is just x in my, favorite half plane. And so all I really need to do is understand in that half plane, I just need to understand this equation, x plus z squared minus 1 equals 0. And we have a little algebra 2 problem. And, just looking at the structure of this thing, you can see this is a parabola. And, okay, now you got to remember your algebra 2, and so this opens into the x direction because x is equal to z squared, and then a minus 1. Think about the plus 1 and the minus 1. If you want to move things around, your preference, knock yourself out. The punchline, though, is that in this half plane, the parabola is a parabola that has a vertex there and kind of opens that way. It opens in the negative x direction. All right? Now, don't forget, our rule was we consider it in the half plane. You were confined by this. You have to consider it only in the half plane. And that is because it is only in the half plane that you can make this argument. Now keep in mind our argument was square root of x squared plus y squared was square root of x squared because y was equal to 0. And that's absolute value of x because that's how square roots work. And then we asserted that this was x, but we could only make that argument because we knew x was not negative. Right? So, only because we're assuming we're in this half plane, not the whole plane, only because of that can we replace this terribly ugly radical with our nice, cute, pretty, simple little plain old x. Otherwise, we're stuck with this absolute value of x, and remember, algebra of absolute values is super annoying and confusing, and we don't want to do that, right? So very importantly, what I've actually concluded here is that my surface is not a rotation of this whole parabola. That whole parabola does not fit inside of this half plane. We're looking at the cross section only in the half plane. I know the half plane will be enough. Whatever that half plane intersects, that will rotate to make our surface. This outer part of the parabola is not in the half plane, so we lose it. Right, it is only this part of the parabola that is that cross section. So that's the curve that you rotate around the around the z-axis, and so you get the football-like shape that I'm showing there. Everybody good? Yeah. Yeah, I'm a big fan. I love symmetry arguments, whenever x and y appear only as part of this special form, you got yourself a symmetry, and I don't want to say always. But yeah, it's bound to be. I mean, I could probably dream up some wacky counterexample where something really weird happened. I'm having a hard time off the top of my head. I think symmetries are almost certainly going to be the best way to argue it. Yeah. Okay. All right, but don't forget about this half plane business. If you do take this whole thing and, kind of continue, notice that would make a shape where Z can get up here, would get arbitrarily large and arbitrarily low. Right? And that's nonsensical. Look at the original equation. Our original equation, what would happen if Z is big? If Z is big, we would have a square root, which is clearly positive, plus something big. And this paltry little -1 is not going to help you get back to 0. Right? So clearly Z can never be bigger than 1. Right? And so anyway, be careful with the half plane requirement. Okay, there's a whole bunch of other examples in here, and I'm going to let y'all read through these examples that take a bunch of time. Again, we've got to move along, but I do encourage y'all to read through these other examples. I want to point out, though, that there are analogous arguments. Someone may have asked about this earlier. I can't remember. But there are analogous arguments about other planes. So, for example, if Y and Z appear only as part of that special form, well, that special form tells you about distance to the x-axis. And that means that when you rotate a point around the x-axis, you're not going to be affecting, you're going to get a bunch of different y's and z's, but you're not going to be affecting how the y's and z's participate in the equation. And the resulting surface is symmetric around the x-axis. And then you can look at a half plane hinged on the x-axis, understand that curve, and rotate it. So there is an x-axis version of this symmetry argument, and then analogously there is a y-axis version of this argument. Totally analogous. Real quick, let's look at this one. So at a glance, you see that there's an x squared and a y squared, and perhaps you're hoping that maybe we could just use a rotational symmetry argument around the z-axis. Maybe wouldn't that be nice? But notice x and y do not appear strictly as part of the special form. That's x squared minus y squared. That's not close enough. It's got to be rigidly, strictly, exactly square root of x squared plus y squared, and functions of that. So likewise, y and z do not appear in the special form, but x and z appear only as part of the special form. Right? And so we have a rotational symmetry around the y-axis. And you can think about what this looks like in a certain half plane. Now I'm going to pick this half plane here, this being the half plane where x equals 0 and z is greater than or equal to 0, at which point square root of x squared plus z squared is just equal to z. Right? That makes this equation simplify very nicely. We get just that. And this is a hyperbola, and I refer you back to all of your memories of Algebra 2, and you got to remember which way does the hyperbola go. Okay? Something to think through, make sure you're straight on which way the hyperbola goes. This hyperbola goes, this hyperbola, with the highlighter. Here we go. Hyperbola is like this. Oh wait, we only want the part in the appropriate half plane. Not that it matters in this case. But you take this hyperbola, you rotate it around the y-axis, and what you're left with is this kind of, I don't even know how to describe that shape. Yo-yo. It's kind of a weird shaped yo-yo, maybe? A little weird yo-yo shaped surface. Yeah? Okay. All right, a bunch more examples in here. I encourage you to take a look. And, of course, a bunch of exercises. I am going to pare this down a little bit. Some of these are a little repetitive. But anyway, you'll get plenty of practice. Okay, moving along. I want to go back and talk about functions a little bit. The next 3 sections really are kind of really about functions, how to represent functions. Remember, we have our old friend from single variable calculus class, which is, the graph of a function, and we use graphs so much and so exclusively, some students don't even realize there's a difference between a function and the graph of a function. It's just, I don't know, it's every time you have a function, that's the picture you draw, it's an easy confusion to make. In general, you find yourselves drawing pictures kind of like, kind of like that. Okay. All right. So I just want to point out that is not the exclusive and only way to represent a function with a picture. There are others, and graphs, great as they are in certain circumstances, are pretty limited in certain circumstances. And I want to just walk through the details of this. First of all, what precisely is the process by which we construct a graph? It's arbitrary. So let's get detailed about exactly what is this deal so that we can then critique it as we go along. So here's the process. If you have a single variable function, single variable function such as this, and let me take a moment to recognize that is a single variable function. A lot of people would say, hey, wait a minute, there's 2 variables because y is x plus 1 and x is a variable and y is a variable. This is a little too quick. This is premature. Where's the y of which you speak? Right? I've got a function here. Domain is R1, target is R1. If you give me a variable, I have to have a variable named x so that I can describe what goes into this function and what the formula is for what comes out. But this thing that comes out, x plus 1. I have a name for it. The name is f of x. We don't need to call it y. Right? So, as it stands, there is 1 variable in this story. All right. So to form a graph, we choose to introduce a new variable. That's a choice. It is not required that we have to do this because it's a function or something, right? That doesn't make sense at all. We are choosing to create a new variable. Next, we are choosing to set this new variable equal to the output value of the function. That's a choice, right? And then subsequently, we're going to take this equation and we're going to ask what is the set of solutions to this equation. Right? So here's an example. Let's look at this function here. F of x equals 1 minus x. There's a single variable function, only 1 variable. Never heard of y. Don't know what you're talking about. There's no y. It's just f of x is 1 minus x. Period. Right? I'm going to choose to create a new variable y. I'm going to let y equal to the value of this function, 1 minus x. Now I have an equation. In fact, by the way, notice of 2 variables. I can ask what is the set of solutions to this equation of 2 variables, which you might prefer to rewrite as x plus y equals 1. I don't know. Suit yourself. And here you go. So don't think of this, I suggest, don't think of this as the function. This is not 1 minus x. That's a mistake. This is the graph of 1 minus x. This is the result of an arbitrary and highly optional procedure that you may want to apply to the function 1 minus x. This is not 1 minus x itself. Okay. All right. Okay, so let's do a multivariable version of this, and analogous story. If you have a multivariable function, you can choose to take the output values of that function, choose to set them equal to other variables, right? If there's m different output values, then you'd need m different output, newly chosen output variables. And then you can look at this resulting equation and ask what's the set of solutions to that equation. And let's just go straight to an example. Here's a nice example. Let's look at this one here. Here's a function of two variables. The output, lucky break, has only one value. There's two terms in the formula, right? But this is one formula. This is not x1 comma x2, right? This is x1 plus x2, period. So there's no commas. This is not a list of formulas. It's just the one formula. So that's one output value. I can describe that output value as being what I'm going to set y equal to. Now notice I have an equation involving three variables. My variables in this equation are x1, x2, and y. Equation of three variables. Now here's where you have to use the techniques from the previous section. Some way or another, in this equation of three variables, you gotta, it's rotationally symmetric. Always hope for that, right? It's fingers crossed. I mean, when it turns out to be a symmetry, it's awesome. Sadly, this is not rotationally symmetric around anything. This is not a stretch or translation of something more familiar than this, that I can't simplify it from sort of that point of view. I guess I could take cross sections. You could take the cross sections would be various lines in various planes. But the really easiest way to identify this is to realize this is the equation of a plane, right? It's just, it fits the form. This is, I can rewrite it as, x1, 1x1 plus 1x2 minus 1y equals 0. And so this is a plane that goes through the origin with normal vector 1, 1, negative 1. So, yeah. Got lucky. And here's what that looks like. It's a hard plane to draw because this plane is, it goes through the origin. You can see right there, but it's coming out of the page toward us in a weird way, and it's just hard to represent that. So what I was trying to indicate with these dotted lines here is that this triangle is tilted toward us in such a way that you can see this is sitting directly above, a part of the x1 axis that's toward us. And this is above a part of the x2 axis that's, again, because of tilting forward, kind of somewhat to the right. Okay. All right, let's see a more interesting example. Let's look at this function right here. Now, here we have a function of two variables. I choose to make the graph of this function. I don't have to. We're making a choice here. Notice that here y is one of the input variables. I can't say I'm going to create a new variable y and set all this equal to y, because y has already got a job, right? Y is one of the input variables. So I've got to choose a different variable. Z seems like a reasonable choice. New variable z that I set equal to the output value of the function, thus resulting in an equation. And again, we start playing the game. How can I understand this thing? This one, we're not so lucky as to get a plane. It doesn't fit the form. It's not rotationally symmetric. It's not a translation or stretch of something more convenient. Here, we're going to have to play a cross-sections game. This is a nice exercise. I want to encourage you all to think about this on your own. Think about various cross-sections of this and what they look like. And what you will find is it looks like this. So if you look at cross-sections for constant values of y, you're going to find that you get parabolas, upward pointing parabolas that as you increase c are shifted more and more upward. Or if you want to take cross sections perpendicular to the z-axis, you will find that the cross sections are again parabolas. As you go up, shifted more to the right, blah blah. So maybe a little bit harder to see it that way, but equivalently, that allows you to reproduce this same shape. Okay. All right, so the graph of this function is this surface here. How we doing? Everybody okay? Alrighty. Again, more examples. I'm going to let y'all look at those examples, but this one I do want to talk about. I want to start critiquing graphs now, and here's my big one. Look at this innocent little function. A function from R2 to R2. This is the lowest dimensional domain that I could have without it being a function of a single variable. Right? And then my target, this is the lowest dimensional target that I could have without it being a merely real valued, single valued function. Arguably, this is about the simplest example we could possibly come up with. I mean, it's obviously not quite this simple, but this is not an extreme example, right? R2 to R2. And, well, we have two input variables. I'm going to have to create two output variables to be the names that I'm going to assign to the two output values of this function. Altogether, I'm going to have an equation involving four variables. That means that the graph that I would have to draw of this function is going to be in four-dimensional space, and I just can't do that. I mean, look, in certain ways, I've practiced a lot, right? And I can kind of kid myself sometimes into thinking that I have a little bit of an intuition of, maybe a little bit about what four-dimensional space looks like. I'm probably kidding myself, right? But I certainly can't draw it. That's right out, right? So this is graphs are a bad tool in this case. Is everybody on board? Okay. All right. So please do not hang your hat on graphs. It is that's a losing strategy. Okay, examples to do. Now, so what do we do if graphs are not something we can rely on? By the way, let's talk about why did we rely on graphs in Calc 1 and Calc 2? Because we could. Because, well, we had one input variable, one output variable. That gave us two variables for the graph, which is a picture on two-dimensional XY plane. We have two-dimensional paper. It was a perfect little confluence of conveniences, right? And so, yeah, graphs are awesome in single variable calculus. But you see now how they're not for multivariable. By the way, I'm now looking at the clock and realizing that it is this is a pretty good break time. So why don't we break for 10 minutes starting now, and we'll pick up here for talking about level sets in a few minutes.